Hi students, welcome to my lectures on chemical reaction engineering. In the today's lecture, we are going to discuss about just a basic introduction to different reactors we are going to deal with. Okay, there are basically 4 basic reactors. One is batch reactor, second is CSTR, that is nothing but continuous stirrer tank reactor, and 3 plug flow reactor, and 4 packed bed reactor. Okay, these are the 4 basic reactors normally we discuss about. In every reactor, the agenda is to find out different parameters. Example, entire CRE crux of the CRE course is to design a reactor. Design a reactor nothing but size of the reactor. Finally, you have to find out the size. Okay, and the basic reactors which we discussed is batch reactor. That means a fixed volume container will be there. You are going to put on some molecules of A, that is my reactant, and after some point of time B molecules will form, that is my product, and few unreacted A. So agenda here is to find out in a batch reactor what is the time required for given conversion, that is to convert 80% of the reactant to product, what is the time? You have to use this equation. In this equation you have to integrate. Okay, integrate Na means final moles of A to the initial moles of A into DNA by rate into V. V is the volume of this particular reactor. If you use this equation for a given conversion, what is the time that is required, you have to find out. Here it's a stirrer tank reactor, means it's a non-flow reactor. Batch reactor is a non-flow reactor, it's a flow reactor. Here you have to deal with volumetric flow rates, molar flow rates. Example, there is a container fixed with a stirrer, okay, and the initial concentration is Ca0, initial molar flow rate is Fa0, initial volumetric flow rate is V0, exit molar flow rate is Fa0, exit concentration is Ca, exit volumetric flow rate is nu. Okay. Then what is your agenda? For a given conversion, what is the size of the reactor that is required? That means you have to use this formula. Agenda is to find out the size. Size means volume of the reactor. For this flow rates, this conversion in other sense, what is the volume that is required? Then the formula is V is equal to Fa0 minus Fab minus rate. Rate is the speed of the reaction. And here the plug flow reactor. Here it's a simple tank. Here it's a kind of pipe. You can talk long tube you can think about. I am sending some reactants and some products or unreacted A is coming out. Initial molar flow rate is Fa0, Ca0 is initial concentration of A, V0 is the initial volumetric flow rate. Fa is the final volumetric flow, final molar flow rate of A. That means here Fa0 initial flow A, Fa is the final volumetric flow rate, molar flow rate of A. Ca is the final concentration of A, and nu is the final volumetric flow rate. Okay, this is what. And here also your agenda is to find out volume of this plug flow reactor. The reason it is a plug flow reactor is because the velocity in a pipe, as I have cut the pipe, okay, I am started to measure the concentration, velocity here, 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 here. At every corner the velocity is the same. That is why it is called plug flow. That means this is called plug flow reactor. Okay. Here also agenda is to find out for a given conversion what is the volume that is required. Here it is a kind of similar to the plug flow, but here the catalyst is there. Okay. Imagine a long pipe filled with a catalyst. Now the reaction happens on a catalyst. In such cases, initial molar flow rate of A is Fa0, initial concentration of A is Ca0, initial volumetric flow rate is nu0, final molar flow rate is Fa, final concentration of A is Ca, final volumetric flow rate is nu. Okay, that means for this conversion, what is the mass of the catalyst that is required? You can use this W. Okay, W is nothing but integral final molar flow rate to initial molar flow rate dFA by minus rate. Okay. For the plug flow reactor and the for the batch reactor, for the packed bed reactor and plug flow reactor, you have the integral. For CSTR, you don't have integral. We will discuss about why you don't have any integral. Rest all the three have the integrals. And you can see in every expression, in every design equation, these are called design equations. In every design equations, there is a called rate term is there. That is what we have done till now. Because we have gone through many different kinds of reactions, zero order reaction, first order reaction, second order unimolecular, second order bimolecular, and reversible reactions, autocatalytic reactions, non-empirical reactions. All the effort we have done till now is to design a reactor. If you know the rate, that means then you can design any reactor. That means if it is a zero order, substitute in place of rate, which is K. If it is a first order, substitute only KCA and integrate. And if it is a second order, example, anything, if it is a second order, substitute in place of rate KCA square. Like that, if it is a reversible reaction, substitute in place of rate K1CA minus K2CB. Like that, you have to substitute the appropriate rate expression to design any reactors. That is why whole agenda. And one more extra thing I want to discuss about is, as long for the constant volume, that means if I fix the volume, it's called a constant volume. If I fix the flow rates, it's called constant flow rate. That means constant volumetric flow rates. As long as volume is constant or volumetric flow rate, that means initial volume is equal to final volume, initial volumetric flow rate is equal to final volumetric flow rate, there is no issue. If final volume is different from initial volume, final volumetric flow rate is different from initial volumetric flow rate, and more a bit extra expressions will come. Those extra expressions are, because rate is nothing but, example first order, rate is nothing but KCA. Then what is KCA? What is CA? CA comes from here. Let us example, for the constant volume or volumetric flow rate, what is going to happen? V is equal to initial volume is equal to final volume. Final volume is equal to initial volume. Final volumetric flow rate is equal to initial volumetric flow rate. Na, you know from the stoichiometry, Na naught into 1 minus x, x is the conversion. Concentration, final concentration is nothing but, that means any of the concentrations. Final molar flow rate divided by final volumetric flow rate. That is nothing but Fa. Because nu is equal to nu 0, I can replace nu with nu 0, nothing but Fa0 into 1 minus x by nu 0, Fa0 by nu 0. Initial molar flow rate divided by initial volumetric flow rate, you get initial concentration. So Fa0 by nu 0 is nothing but Ca0 into 1 minus x. That means final concentration is equal to initial concentration into 1 minus x. You know conversion, Ca0 minus Ca by Ca0, everything is fine. What happens if my batch reactor volume is changing? In other case, what happens if my final volumetric flow rate is different from initial volumetric flow rates? Generally, this happens because of the gas phase reactions. You know, one liquid phase reactions, there is no issue. For the gas phase reactions, the more volume will come. Why? Because 1 mole of A is giving 1 mole of B, no issue. 1 mole of A is giving 2 moles of B. That means because of the reaction, 1 mole is giving 2 moles. Suddenly the moles will increase, because of this volume will rise or volumetric flow rates will rise. That means initial volume will different from final volume. Initial volumetric flow rate is different from final volumetric flow rates. So in such cases, you need to take care of that volume expansions or volumetric flow rate expansions into picture. So one way of handling is to find out epsilons, because I have given a detailed explanation of the epsilon in my stoichiometric lectures. So let us see what changes is going to happen, because agenda is to find out what is CA, because finally I have to substitute here. What is the CA? Example, final volume is equal to initial volume into 1 plus epsilon into x. Final volumetric flow rate is equal to initial volumetric flow rate into 1 plus epsilon into x. That means final concentration. is equal to final molar flow rate divided by final volumetric flow rate. Final molar flow rate is equal to Fa naught into 1 minus x. Final volumetric flow rate is equal to nu 0 into 1 plus epsilon into x. I know Fa 0 by nu 0 is equal to Ca 0. That means Ca equal to Ca 0 into 1 minus x by 1 plus epsilon x. See here, there is no 1 plus epsilon x term is there in the denominator. Here you additionally you have the 1 plus epsilon x in the denominator. Here the conversion is the same everywhere, because finally you have to design the reactors. For you to design the reactor, you should know what is the rate. Rate, inside the rate you have the concentration, then what is the concentration? Here are the concentration. If it is a constant volume, this is the concentration. If it is a variable volume or volumetric flow rate, you have this is the concentration. Once you substitute everything, you find out, design or integrate it and design the reactor. Okay, let us go into the deeper details that how I got these equations, and with simple examples let us design a reactors. Okay, thank you very much. We will meet up with the next lecture.